Sure. I'm fine. So our next talk will be by Omar Kihel from Brock University. He will tell us when is the ring of integers of a number field coverable. So go ahead, Omar.
Okay, so give me 1 minute. Can you see my screen? Can you see my screen, guys?
Yeah.
Yes, we can see it.
Okay. Okay, so hello guys again. So my talk would be about coverable rings. I gave a talk in Ottawa at the honor of Lang Langs, and the title was the same, but I said my talk today would be a little bit different. First of all, I would like to thank the organizers, all the organizers, and the organizer of our number theory session, so Florian Lucas and Claude Lerevec, for giving me the opportunity to talk in Buenos Aires. Let me start from something very easy. Okay, so question number one, this question, we can find it in any or many books of first year or second year algebra, is one is a group, the union of two proper subgroups. So the answer to this one is very easy, and the proof any undergrad student, any good undergrad student can do it. You can do it by contradiction. Suppose that G is the union of two proper subgroup H1 and H2. So you take A in H1, but not in H2, B in H2, not in H1. So A times B is in none. Okay, so easy. Now there is another question. The next step is one is the group, the union of three of its proper subgroups. So this is less obvious, but still not very difficult. I wrote it as difficult question because the second part of the proof is difficult. So the first part of the proof is, so the theorem is this: a group is the union of three proper subgroups if and only if it has a quotient isomorphic to C2 cross C2. Is here C2 is Z over 2Z. C2 is the cyclic group of order 2. So the first proof is the first direction is if G is our group that has a quotient G over N isomorphic to C2 cross C2. So then G over N, which is Z2 cross Z2, is the union of the three subgroups that it has. So H1, H2 of all them are of index 2. And then what you do, you take the inverse image of H1, H2, H3 under this surjective homomorphism, and then you obtain three proper subgroup of index 2 in G. The other direction is difficult. It's not difficult, it's technical, but in the meantime, beautiful. I'm not going to give it to you here. So people we said, okay, maybe we can generalize the idea to other n. Is it possible to write a group as a union of n proper subgroups? What are the conditions? So this Skora theorem was like in 1916. Until that time, so we had the result of Kahn. So let me give a definition here. Let G be a group. G is the union of n of its proper subgroups, but is not the union of any smaller number of proper subgroups. So we write sigma of G is equal n. So the length of the number of proper subgroups that are the minimum that are needed. And as I said, our groups may be finite or infinite here. So theorem here, as you can see, Kahn's extended Skora theorem. So let G be a group, then sigma of G is equal 4, if and only if sigma of G is not 3, and has a quotient isomorphic to the symmetry group S3 or C3 cross C3. So as you can see, for 4, a part of it is similar to sigma G is equal 3. So you see C3 cross C3, but you see something else. You see S3 as well. For 5, it's completely different. So sigma G is equal 5 if and only if, of course, sigma G is not in 3 and 4, or 4 is not equal 3 or 4. And G has a quotient isomorphic to something completely different, to alternating group A4. Now, sigma G is equal 6 if and only if sigma G is not 3, 4, or 5, and G has a quotient, so either D5, C5 cross C5, or here the W is the semi-direct product, so it's not C4 cross C4, it's semi-direct product, C4 cross C5, semi-direct product. So as you can see again, for 6, part of it, so C5 cross C5 is similar to Skora's theorem, but the other groups are different. Well, and Kohn stopped here, and he made a conjecture, but he could not prove it. Then, a few years later, you have the theorem, this theorem proved by Tompkinson's. So, because people asked, what happened for sigma G equals 7? Can we apply the same ideas? Can we have a similar result? And when you see the theorem, there is no group G such that sigma G is equal 7. So the first time I saw this result, I was kind of disappointed. Disappointed because I thought, well, I mean, there is no hope, or at least there is no obvious hope to generalize these kind of results. You know, sigma G is equal 7. So what is happening? What is behind? But I was wrong. It was not true because of the result of Bargava here, Bargava 2009. So what you have for any positive integer n, there exists a unique minimal finite set, Sn, of finite groups, such that sigma G is equal n. So in general, if and only if sigma G, of course, is not 3, 4 until m, and G has a quotient isomorphic to some group K in Sn. So what is here? So if we go here for sigma G equal 3, 4, 5, 6, we see the theorem of John. But what's happening for sigma G equals 7? So for even if you look at the proof of Tompkinson's result, you will see that in the proof it's implicit to see if sigma G is equal 7. It reduces to see if G has a quotient isomorphic to a list, to a finite list of groups, which is Sn. So from a theoretical point of view, this result is beautiful. From algorithmic point of view, this result is so far is not nice because of what I'm going to show you now, because of this theorem. If K is in Sn, then K is less or equal n factorial. N factorial is very large, right? So the order of your group is very large. If you take K is equal 20, so there is no hope to see all the groups less than or equal 20 factorial order, and then you check by hand or by computer. This is very large. This bound of n factorial has been improved, but not that much. So you have something like n minus 1 factorial, or if I am not wrong, until n minus 2 factorial. So when n is small, this is a good improvement, but when n is large, this is still not good. The proof of the result that I showed you uses what is called Neumann results. And I will show you this Neumann result because this is something that I will, or similar to that I will use for ring. So what it says? It says, so first of all, we say that a group G is an I-redundant union of subsets in general AI. If G is a union of AI and no IG is extra, it means you cannot take any AG. I am not saying here that this union is minimal in terms of length. I'm saying that you cannot take away any AG, okay? So this result says if G is an I-redundant union of subgroups AI, then the index of the intersection of the AI in G is bounded. And what is most important is that the AI, each one of them has finite index. And for me, this is amazing result. So if you can write G, finite or infinite group, as a union of finitely many subgroups, then each one of them has a finite index in G. You cannot take, you cannot bring another one which has no finite index. So Why this is important, you will see it in terms of group, in terms of rings. Okay, so when you see the result of Tonkison sigma g is equal 7, there is no group such that sigma g equals 7. People said, oh, maybe we put a wrong generalization. Maybe the question, we should put the question differently to have nice generalization. So they put the question that way. One is the group, the union of its proper normal subgroups. For sigma g equal 3, as we saw, H1 and H2 have index 2. Yes, sorry? Is there a question or something? No? Okay. So for sigma g is equal 3, when you have g is equal H1 union, H2 union, H3, we saw that each one has index 2. It means normal. So we are in this situation. And we give a definition. So let's eta g is equal n if g is the union of n proper normal subgroups, but is not the union of fewer than n normal subgroups. And then there is this theorem. Suppose that a group G is the union of its proper normal subgroups, then eta G is equal to P plus 1, where P is the smallest prime such that G has a quotient isomorphic to CP cross CP. So here you see we have CP cross CP if such a prime exists, and eta G is equal to F. So if you take P is equal to, you have score as a result, right? So eta G is equal to 2 plus 1 is given 3 if this. And the corollary for finite group, a finite group is the union of proper normal subgroups if and only if it has a quotient isomorphic to CP cross CP for some prime P. This corollary is still applied for infinite group if we know that G is a union of finitely many normal subgroups. Okay, so I think this is a nice result. Now, what about rings? Of course, we know that if you have R ring, so to have the same idea, is it possible to write it to read it as union of proper subrings? If R as a group, additive group, you cannot write it as union of proper subgroups, so then you stop. You cannot. There is no hope to write it as a union of proper subgroups. But what if? I mean, what if you can? You know that you can write it as groups. So what happened as rings? So Lucchini and Marotti in 2012 described all rings with covering number 3. It means all rings are that you write as union of 3 of proper subgroups. We have them all. Okay. In 2017, Renan wrote a nice, very beautiful paper where he dealt with finite and semi-simple rings. So basically, for him, so what is a finite and semi-simple ring? As you know, that a semi-simple ring, there are many equivalent definitions, but you can look at the finite direct product of simple rings, so which is a ring of matrices over a division ring. But since he dealt with finite, so it will be the product, a finite product of ring matrices over a field, right? We are in a finite case. And he solved the question completely in a nice way, beautiful way. Before telling you our results, so the most important thing we thought about it, what happened for ring of integers of number field. So if you take number field K and you look at the ring of integers, is it possible to write ring of integers as union of a finite number of subrings? And before giving you this, the result that Ayad, my collaborator from France, and myself proved, we have necessary and sufficient condition, I will give you some easy result before. So the same definition here, sigma, so I'm moving because I don't want to, okay. So here, you remember Neumann's result that I told you is very important, and using this result, we can prove. So here, if you take R coverable ring, it means a ring that you can write as union of proper subrings, such that sigma R is finite. Then what is important, see, there exists a two-sided ideal I of R Here I'm saying two-sided. We don't suppose that our rings are commutative. And when we talk about subrings, we do not suppose that the subrings contains a unity. Okay, so like that, the ideals can be part of the covering. Okay, so in the weakest form here. So then there exists a two-sided ideal R such that R over I is finite, and the length of sigma R, sigma R is equal to sigma R over I. So basically, if you can find such an ideal, or say it in other words, this result reduces somehow the question. Instead of talking when you have R an infinite ring, reduces to talk about finite rings, provided that you can find such an ideal. But we know that such an ideal exists if, of course, sigma R is finite. Okay. So here, for R a ring and A an element in R, we take this subring here. So double bracket here containing R are those forms CNAN plus CAA, and there is no misprint. I am not missing the constant term here. Okay, so the last one is C1A, where the CI are integers. Here you can check easily that this is a subring, and this subring is contained in Z, bracket A, right? And why this is important? For example, I give you examples. If you have a finite field and you ask me, is this finite field coverable as a ring? And the question is, the answer is no, because as you can see, if you take the multiplicative group is cyclic, and if you take one generator has to be in one ring. If you take F is, imagine that FU is R1 unit to be in one of those rings, and if generator is there, then it's the complete ring itself. So, can you still hear me, guys? Can you still hear me?
Yes.
Okay, thank you.
Yes, we can hear you.
Okay, thank you. Now, if you take this are an easy example. So if you take F2 cross F2, of course, in the Werner paper, they did. I'm giving you here only easy examples, but we know the answer if you take FQ, product of finite fields. Is it coverable or not? They have necessary and sufficient condition when they are coverable or not. But here I'm giving you just examples. So if you take F2 cross F2, then sigma is equal to 3. This is something we know already from Scholar's result, right? Anyway, so I think I will move quickly. Okay, here, for example, there is a result of Ayad, myself, and my former student, Laron, former student of Claude Lévesque, Antonio Lé, and myself. The first one is just an example. The periodic integer ZP is not coverable, but the finite number of its proper rings, and so on. Okay. I think I will move. For example, if you take R coverable by quantably infinite number of subrings of finite index, if you suppose R Artinian, then R admit, and so on. Okay, before going to the main result, I would like to ask you a question that I don't know the answer, so maybe you can help me. Is it possible to write a ring that we know that it's non-monogenic in the form, this form union of zeta, theta, I from 1 to infinity? Of course, we know that this is possible with time, but here under the condition that every theta I is primitive. Is it possible to do that? I have no idea. I know example where it is possible, but I don't know any example where it is not possible. And the next question, if this is possible, is it possible to extract a finite union from this infinite union? A finite union as this one where every theta I is primitive. I have no idea. So I have examples, so let me move. But we have this result saying if R is union of z theta I from 1 to n, and the other one z theta alpha j from j1 to n. Here I don't suppose that theta I or alpha j are primitive, but we suppose that are minimal. Minimal, not in terms of the land here, minimal in terms of redundant. So here we can prove that n equal m. So basically n and m, I can look at it as an invariant of the ring. And we proved this result, that if this is possible and I call this one L, then we have this inequality. L is bigger than what you have here. Okay, so I think in order to stop at 11:30, I will move here. Okay, so this is the main result. How about rings of integers in a number field? So before this, let K be a number field of degree n, A is ring of integers, and A had the set of element A primitive over Q. And here you take theta in A if and f theta x is the characteristic polynomial. If theta is primitive, then this is just the minimal polynomial of theta over Q. And d sub k be the absolute discriminant of K. We know that the discriminant of theta is equal I of theta squared times the discriminant of the field, where I theta is the index of that theta in A. Okay, and we can define what is called the index I of K of the field K, which is just the GCD of I theta, where theta are primitive, right? Theta are in A hat. Now, there is what is called the common factor of indices. So a common factor of indices is a prime P such that divides I of K. And if you know some of you were teaching algebraic number theory, and for students, we give them what is called Didriking theorem. And we say, if you would like to factor, to take the factorization of P, a rational prime in A is a ring of integer of a number field K, we tell them most of the time, suppose that P does not divide I of theta. And if P does not divide I of theta, then the factorization of P is the same as the factorization of the minimal polynomial of theta. And some students are, oh, what if it divided? And we just tell them, oh, take another one. But sometimes there are some primes that call common factor of indices where P divides I of K. It means why P divides I of theta for every theta primitive. So what to do? Of course, there are some difficult results, and explain how to do the factorization. It turns out that these primes here have an important role in whether or not the ring of integer, you can write it as union of a finite union of proper subrings. So I will give you the result only, and I will stop. So the ring A is finitely coverable if and only if one of the following two conditions hold. The number one, so this result is with my collaborator Ayad, there exists a prime number P, which is a common factor of indices, or common index divisor, we call it. And the second, so one of the two, the second condition, it tells you if the first one is not satisfied, there should exist a prime P such that the number of prime ideals of A lying over P and having the residual degree equal F, this number, okay, I put it away. There should exist a prime number P such that the number of prime ideals of A over P, dividing P in A, and having the residual degree F equal 1 should be at least equal P. So we have a necessary and sufficient condition, plus that I will not give you here because we have a way how to compute sigma of A. In the case that one of these two conditions is satisfied, then is coverable by a finitely many subrings, and we know how to find sigma A in terms of this prime and so on. So I think I will stop here, although I started late, but in order to keep up. Okay, thank you guys.
Thank you very much, Omar.